We have a few more to go through. So again, my name is Doug Shakshober. I'm the Director of Performance Engineering at Red Hat. And
You don't have to go.
you want to introduce yourself again?
It's all the same people, I think, right?
Are you guys all the same people? Oh. Okay. Any new ones? Larry Woodman is our VM, one of our lead architects on the virtual memory. And yeah, we're going to go through these other topics. Again, some of them we've been through. A lot of these are all things within RHEL 6, quite a bit of differences between RHEL 5 and RHEL 6. And like the last session, we'll try to hint at new things that, that may be coming or that we're working on upstream with the team. So a big improvement or a big addition that came out in RHEL 6 is the ability to essentially have a Cgroup infrastructure so that you can carve up systems to essentially impose a bunch of different controls on not just, we covered basically NUMA control, and so that's CPU and memory, and those tools have been around for quite a while in 4, 5, and 6. But now we can also do things like control network and disk. Both you can carve up sharing a same device with different applications, and not only can you control the device, you can actually change the weight factors. So we want application A to get 80% of a 10 gig network, and application B can only get, we can limit him to only 20% of that network. Same thing on the disk I/O. So whether it's a controller to share. So once you start doing this level of control, you can actually, other subsystems can start using that. So in fact, virtualization with KVM is pretty much possible now to use this infrastructure to get better placement and optimization, et cetera. So the example here of, we have a couple of virtual guests, but we can also still run things on the host.
You have to point it to that.
Gotcha. Okay, so going to the keyboard here. So the bottom line is you can run bare metal applications. So we are starting to see some people run virtualized systems on especially 2, 4-socket systems. You have enough horsepower. You can run some of your guests. You can run some of your testing on a couple nodes. And the other thing that it does is it insulates the host from bogging down your mission critical applications potentially. So, whoops, geez, even on the keyboard. So again, the architecture allows things. It's hierarchical in nature. Larry's going to step you through I think they're really good examples, because in the end you can take the deck home. You can then implement it yourself. Get enough use patterns, but the idea is we are running app A, say you're in bare metal and it uses a Cgroup. We can run KVM guest 1 or 2, and then even within a KVM guest you can actually specify Cgroups within its, say, 32 CPUs. The case C here uses 16 CPUs for a guest, and within that 16 CPUs, you can basically treat the guests just like bare metal.
All right, so first of all, I wanted to say, we actually out in the Red Hat booth have a demo on Cgroups. So we've put together some extensive applications to show you how to use Cgroups and the benefits of doing so. The Cgroups allows you to subset your system. If you have a big 64 CPU terabyte system and with all kinds of drives and I/O capacity and network capacity on it, you can go in there and you can create a Cgroup that says this Cgroup gets this amount of memory, this much CPU horsepower, this much disk I/O bandwidth, this much memory this much network bandwidth, and run applications in that. And if that overwhelms that Cgroup, that's all it does. All it does is overwhelm the Cgroup. The rest of the system runs without being affected. So new to rel 6.3 is the default mount points of the C group is defined in a file in etc sysconfig.conf, and that will determine where the C groups actually get mounted and how you go about using them. So once again, if you come to the Red Hat booth, I'm there until 6 or 6:30 or something tonight if you want. There's a lot of power in C groups, and more than I could really show here. But a typical example of how to use them is I have a, guess not, I had a 16 gig 8 CPU system in my office, and what I did is I wanted to create a subset, which is a gig and 2 CPUs, and then I wanted to write a couple applications and sort of show how it works. And how you do this, I don't know what the hell. Oh, there it goes. Okay. So the first thing to do is a NUMA CTL minus hardware to get a picture of what the system looks like, and then build your C groups based on what the system looks like. If you do it wrong, you're going to create cross-memory accesses and have performance problems. So you mount the C groups, or they're mounted by default now in 6.3. You create like a test area. You CD into the area, and then you set up the memory nodes that you want to use, the CPUs that you want to use, and the limit in bytes of memory. And then you say, I want all myself and my child processes to run in this new C group. So here's an example. I did a NUMA CTL minus hardware. You can see there's 2 nodes, 8 gigs on each node. CPUs 0 through 3 are on nodes 0, 4 through 7 are on nodes 1, and the typical distance thing here. So what I wrote is a program, pardon the name, fork-off. I said I want to create 100 processes, each one. So I created 1 gigabyte of memory in 2 CPUs. So this should basically allocate 2 gigs of memory. And in this fork-off program, I said create 100 of these, 20 megabytes of each, so this would be 2 gigs of memory, and I want to run it on just 2 CPUs. And you can see that it's running on 2 CPUs. It overcommitted memory, so it started swapping. It swapped out everything that it needed, yet the total amount of memory free is only down from when it started by 1 gigabyte, because that was the size of the C group. C groups allow you to subset in terms of absolute numbers, so you can say I want CPUs 0 through 3, I want certain amounts of memory, I want these disks and so forth. You can also do it by shares or percentages, so you can say I don't care what CPUs I get, but I want 40% of the CPU power, I want such a percent of disk I/O bandwidth and so forth. And so after I did this something to show you how this interacts with NUMA. In order to verify the bindings, we echo a 0 into MEMS and a 0 to 3 into CPUs. So if we go back, we remember that the NUMA CTL minus hardware said that on node 0 is CPUs 0 through 3. So if I do a NUMA stat before I run this, I see the number of hits. I run the program and measure the time, and then you can see that 4 gigs of memory is the program that I wrote. You specified the number of gigabytes. 4 gigs of memory is about 1 million pages. So you can see the NUMA hits on node 0 increased by about 1 million. And the misses, there were no misses whatsoever. And it took about 1.6 seconds to run the program. And if I go and change the binding, so I make cross-memory references here and do the wrong thing, I do once again, a NUMA stat to get the statistics, run the program. You can see it slowed down by about, 1/3 of a second. And you can also see that it made cross-memory references here. So that million memory references are now misses on node 1 because I bound it that way. So C groups allows you an enormous NUMA control as well. It allows you all the same functions as NUMA CTL, but it allows you to do it in buckets so that you can move stuff around. And that's kind of what that NUMA-D program does. You want to talk about this?
Yeah, well, this is just an example again of one of there's probably 4 or 5 interesting examples in Sanjay's database talk, but the bottom line in this case is he has this red database, say the OLTP, say a decision support database, and OLTP is blue, and so during the day we want to give priority to blue, so he basically is just changing the policy, the weight values essentially within that C group, and then a small script you can write, a cron job or whatever. So OLTP by day and decision support by night, without ever shutting your applications down. And by the way, you can literally starve. We've gone to the extremes on a lot of these as well. So, and again, this is done either by varying CPUs, by varying memory, by using C groups with network controllers if you don't have, if you have a shared controller, and also disk controllers as well.
Right. So
you doing that? Yeah. Okay.
So that's sort of where we went with NUMA. Once again, I have in the Red Hat booth we have a demo with a bunch of C group showing how you can control various aspects and how it controls the performance and affects the performance of various applications. A good example of that would be if you have a database and at the end of a trading day, you need to do a backup while the database is active. That's historically been a problem for Linux, for a lot of Unix systems. They have global page replacement algorithms, and you do that backup and it just overwhelms the system and slows the database down while the backup takes place. In order to prevent that, one of the solutions that a lot of customers use now is they put the backup in a C group. In the C group, they limit the I/O bandwidth, the network bandwidth, the memory, and even the CPUs. So the backup might take longer to run, but it doesn't affect the actual database during the trading day. So now we just wanted to spend some time talking about sort of focus or shift the focus a little bit to tuning systems that are not necessarily NUMA, or they might be NUMA, but they might have other issues involved, like CPUs, memory, and so forth. So basically, I just have a couple slides here that tell the processors supported in RHEL 5 and RHEL 6, just show how they scale up. There was a scalability slide at the beginning, and the same with physical memory. On RHEL 5, we don't support any more than 1 terabyte. We're limited to 2 to the 40th power, and that can never change without breaking the KBI. So RHEL 5 is not going to run on systems larger than. It'll run on them. It just won't see any memory above 2 to the power of 40. And on RHEL 6, it's up to 2 to the power of 46, which is 64 terabytes. So this is. I had talked before about zones of memory and on NUMA systems. Basically, the first chunk of memory starts. I should ask one thing. How many, does anybody in here use 32-bit systems anymore? Are they? Yeah. There's a couple of them. Okay. All right. They're different, and I can, rather than spending any time, if you get issues with them, I can talk about those after, sort of on the side. But memory starts out at location 0 up to 16 megabytes of memory, or 2 to the 24th power is what we call the DMA zone. That's for old ISA devices that had no IOMMU, and you had to DMA down to the lower 24 bits. And then from that region up to 2 to the 32nd power is what we call the DMA 32 zone. So if there are devices that support 32 bits of IO addressing, but don't support remapping, the buffers have to come from here. And if you look in the slab cache, if you do a cat of proc /proc/slab info, there are buffers that you can specifically allocate. Drivers can allocate if they need to allocate from these zones. And then finally, all the remaining memory we call the normal zone. And on a NUMA system, this differentiates node 0 from all the other nodes. If you have a 4-node NUMA system that has, say, 32 gigs of memory on it, it's going to be different in that node 0 is going to be split in half. It's going to have the first 4 gigs is DMA, and the second 4 gigs of that 8 gig node is going to be a normal zone. So if you go to allocate from there, the system might or might not, if you allocate and use all this memory, it might or might not, depending on how the system is tuned and set up by default, spill over and start using this memory. And I'll talk about that in a minute. So when systems run, anyways, as far as memory is concerned, I'll skip the 32-bit stuff. The normal zone of memory is basically user allocations. The kernel and user allocations come out of the normal zone, and we postpone using the DMA zone until the absolute possible minute, just in case somebody else needs it. And this can cause problems, and we'll talk about that in a minute. As far as memory pressure is concerned, at boot time, the kernel lives in physical memory, obviously. Its text, data, and BSS, and its config parameters determine the size of these regions of memory. There's nothing you can do about this. The kernel lives in memory. It's got to be in physically contiguous in resident memory all the time. There's no shrinking of it. But then when the kernel runs, it allocates kernel data structures like task structures and various memory and file system structures. These come out of the slab cache. They're dynamic, and you can actually tune how aggressively the system reclaims the slab cache memory if it needs to. If you have a system that's very memory sensitive, it might be beneficial to tune your system so that it aggressively reclaims the slab cache and gives the memory back. The downside of doing that is if the system needs to allocate and free a lot of kernel data structures, it's going to be slower in doing so. So it's a trade-off. And then finally, the huge TLBFS stuff we already went through. The system does not reclaim the huge page stuff, with the exception of transparent huge pages. It does not reclaim that memory at all. Once you've allocated it, you can't touch it at all. You have to manually go in and free it. And then then user space memory is split into 2 regions, anonymous memory and page cache. So you get a program that runs, the first thing it does is it touches its stack. It allocates anonymous memory. Then it starts opening files and doing reads and writes. It starts allocating file back memory or page cache memory. And then finally, we actually make a distinction between the anonymous memory and the page cache memory. There is tunability between the two. So you can control how aggressively the system will reclaim or swap. How aggressively it will swap and reclaim anonymous memory, and how aggressively it will reclaim the page cache memory. And let's see, the page cache memory. A lot of times we've had customers complain because, I put all this memory in my system and there's none free. The kernel uses every page of memory that it can to cache file system data. And if you open a file and read 1 byte of a file, by default, it'll bring in like 8 pages. It'll just bring big chunks in until it runs out of memory. And it will keep those pages clean and it'll sort of extend the free list into them. But what will happen is if a program runs, it typically doesn't have to do any I/O to get access to file back memory unless it's run out of memory and started reclaiming it. If you unmount the file system. So anyways, the page cache memory is only freed if you delete the underlying files, unmount the file system, if the swap daemon runs and decides it's going to reclaim stuff, or there's a manual way to do it we'll talk about in a couple minutes called drop caches. Anonymous memory is different, on the other hand. If a process exits, it's whatever it had in its stacks, heaps, data, BSS sections is totally worthless to anybody else. So we just simply freeze it all immediately. So anonymous memory is freed anytime a process unmaps any of its address space, or kswapd runs and swaps anything out. So you can see the allocations happen by page cache allocation and page faults, and the reclaim mechanism happens via kswapd, bd, pdflush, kupdate, and so forth, and in the page cache via the mechanisms that I just talked about, and then kswapd and page reclaim is basically the way that anonymous memory is freed, along with unmap and exit. So this is basically a picture of the paging dynamics. I don't want to get too much into this, but there is significant tunability in the system to allow you to control how aggressively the system cleans pages and preps for page reclamation, how you can adjust how much free memory it keeps on hand, you can adjust how aggressively it swaps out, how aggressively it ages pages. And some of these tunables, I'll talk about in a minute, you'll see them in some of the TuneD profiles and in other places, and we'll just sort of go over them. This is how the memory reclaim code works. There are 3 thresholds, high, low, and min. When the free list is above high, it does nothing. As soon as it drops down below high, it basically doesn't do anything until it drops to low, at which time it kicks a background daemon called kswapd, which starts flicking pages out. If you overwhelm kswapd, by the way, there's 1 kswapd per NUMA node, so it's on an 8-node system. If you do a PS AUX, you'll see 8 of them out there running, and there's one of these, and the reason that it's per NUMA node is because it wants to make sure it only touches the data structures that are local to that node. All the data structures for the memory subsystem on a given node are allocated on that node. The page array and everything is on that node, so that kswapd doesn't have to do any cross-memory references at all. And these thresholds are actually tunable. And finally, if you overwhelm kswapd and come down to min, the system will throttle you. You'll stop the program. It'll stop the program from allocating memory and make it do the same job that kswapd is doing in an attempt to get the free list back up to this high threshold. And the lower you are in this chain, so to speak, the more aggressively it reclaims memory. Yep.
Is there any concept of least recently used?
Yeah. Yep. Yes, there is. So before I had talked about split LRU lists. LRU means least recently used. So these active and inactive lists, the pages are ordered on here based on the setting and clearing of a reference bit. So the system has a lot of background activity that keeps these ordered. So by the time a page works its way to the head of the inactive list, it has been touched or referenced a lot less recently than something either here or in the active list. Yes, that's the order that will flush out and the order that will free it. Okay? And then we had talked before about file and disk I/O. When you do read and write operations, the page cache is a write-back cache. When you modify something, when you write to a file, you can write hundreds of megabytes to a file, and it seems to happen immediately. And the reason is all it does is write to memory. And then there is a write-back cache mechanism that flushes data, which is also very tunable, flushes data to the actual device itself. This is any buffered system write is simply a memory copy. All it does is write it from the user buffer, you allocate memory, open a file, write a bunch of junk to your buffer, and then call the write system call. It's just a memory copy. Boom. That's all it does. Comes right back immediately. And as far as the user is concerned, it made it alt to disk. And then there are. Let me just see if we can read this a little better here. There are a couple of parameters that there are a couple tunable parameters that control the flushing of pages from the page cache to disk. They are dirty and dirty ratio, and I think a read just shows that it's a read in the other direction, by the way. I'll talk about those dirty ratios in a second here. Direct I/O, which Shak talked about from a database, bypasses the page cache completely. So if you do direct reads and writes, the DMA operation doesn't happen into the page cache and then copy it into memory. It actually DMAs directly to the disk. There are 2 benefits of doing so. First of all, the additional memory copy that you eliminate by doing this, but also the memory overhead. Using buffered memory doubles the size of all the file system data, and there's a copy of it in the page cache, and there's a copy of it in the user's buffer. So that's why that's one of the reasons a lot of databases will use direct I/O, is because they'll totally eliminate the pressure off in the kernel to constantly reclaim this page cache memory. So as far as the memory management tunables are concerned that you'll see in like TuneD, profiles, and the ones that are most recently are frequently changed are there are reclaim ratios. These control how fast or aggressively the system reclaims memory. There are write-back parameters. These control how aggressively the system flushes data back to disk. And there are read-ahead parameters. These control how aggressively the system pulls data in. So if it says, I get plenty of memory, I got to go out to disk, I'm going to grab 8 pages instead of 1. So just to talk about some of these swappiness, has anybody used this VM swappiness parameter? Most people have mucked with this a little bit, especially in RHEL 5. In RHEL 5, it controls how aggressively the system reclaims mapped memory. Not anonymous memory, but mapped memory. Mapped memory, anonymous memory happens to be mapped, but so is System 5 shared memory that's not using huge pages, and so is any mmap of a file. So if you adjust the swappiness parameter in RHEL 5, it controls how aggressively the system reclaims mapped memory. That is in contrast to RHEL 6. In RHEL 6, we have this split LRU. The split LRU, it means it takes the pages that are on the LRU and it separates them into file-back pages, into anonymous pages. In RHEL 6, swappiness only controls file-back memory. I'm sorry, it only controls anonymous memory, not file-back memory. So the problems that you ran into tuning RHEL 5 in swappiness when running databases are gone in RHEL 6 because this parameter, because the split LRU doesn't touch file-back pages. It can prevent the system from touching file-back pages, and swappiness does not control how aggressively it reclaims file-back pages. So basically, in general, though, this isn't a percentage or anything. It's just some weird arbitrary number. It's 60 by default, and if you decrease it, decreasing it will decrease the aggression in which it reclaims mapped memory or anonymous memory. Increasing it, it more aggressively swaps out or reclaims anonymous memory.
Yeah.
So you can.
So just to iterate Larry's point, because I'm at risk of being swapped out myself. No, I'm all seriousness. So we do want to adjust this in a RHEL 5 system, right? Because what can happen is your page cache can fill up. Again, if you tune your memory carefully or use direct IO based stuff, you probably don't encounter this. But if you start swapping, the world continues to grind, move forward and stuff. But the bottom line is the performance can degrade, and you will see it really degrade if you start swapping kernel structures out in a RHEL 5 system in lieu of just trying to do your file I/O, and heavy file I/O is actually okay because the page lists were one and the same, and so LRU is indeed working. But guess what? When you get back to try to execute something, you may start having to page back in the kernel structures, or you may need that stuff. So the kernel likes to stay around, as well as, there's other stuff that's important. So a quick example here, right? So in this case, with a swappiness value of 60, we're doing file I/O. So how do you tell what's happening here? So there's, how much memory is in swap, free, buff, and this is the page cache value. So you see we pretty much filled up most of memory. When you start seeing SI and SO values, and this gives you a little break too, Larry, this is, you probably start experiencing slowdown, and in fact, block in and block out are directly proportional to, that is the number of kilobytes. So this is running 4 megabytes a second of input and 7 megabytes a second of output. And just by altering the value of swappiness to 10 in a RHEL 5 system, you actually didn't greatly change the amount of memory and cache here, but you've been able to prevent the swapping, and you've achieved about a factor of 4 into 24, factor of 6 here, and a factor of 8 on the output. So if you can keep operating in this mode just by doing some tuning, you can earn those buffalo wings again. So, so I didn't mean to interrupt. You want to go through?
Yeah. So another that controls that controls the reclaim is this VFS cache pressure. This controls how aggressively the kernel reclaims memory from the file system caches. This is like inode. This is metadata. This is inodes and the on-disk data structures. So there are, you'll see the tweaking this cache pressure. The default is 100, which means that it's just sort of a line in the sand. If you decrease it, it increases the, if decreasing this causes the caches themselves to grow, increasing it causes them to shrink. So it just controls how aggressively the system reclaims these data structures. Once again, these are on-disk file system metadata. So if you run into a system that is very memory sensitive, then decreasing this value is probably a good idea to play around with. However, if you decrease it too much, what you're going to start noticing is the file system is going to suffer, because when it goes to do a dentry cache lookup, it isn't there. It's going to have to start bringing all the stuff back in for memory. So this is just sort of a latency versus throughput trade-off here. This min-free Kbytes, back earlier I talked about the 3 different page free thresholds, the high, low, and min. This is the way that you control, this is the way that they are controlled, and this controls basically when the system starts to reclaim memory. These things are set low by default because any memory that's on the free list is not usable to anybody. It's setting these really high has no benefit whatsoever. So, but there are cases in which, like on a system that have the load comes in surges, where you might create hundreds of processes all at the same time, and they do their work, and then they sort of get out of there. It can put the system into a memory deficit. In cases like that, there are times in which increasing this min-free Kbytes solves that problem, and there's some examples at the end of this sort of coming up with this. And this is basically how it, well, this thing kind of got screwed up, but this page's high should be up here, and this page's low should be here, and somebody fell off the bottom here. But you messed up on that. So anyways, this is just sort of a picture of how you could visualize this. In increasing this, by the way, not only raises this to a higher level, but it also increases the distance between each. So min-free Kbytes is high-low is this value right here. So you specify how big you want it, but basically this is twice min and this is 3 times min. So these grow accordingly. In rel 5, actually, and in rel 4, I put in a tunable parameter called page cache, Procsys VM page cache. Its default was 100, and if you lowered page cache, what it would do is it would sort of prevent swapping. So basically what happens is what the system does is it says if 100% of memory is in the page cache, then swap. So if you lower this down to say 10, this would significantly reduce the amount of swapping that was going on as you lowered the page cache. So you could say, I want to keep a certain amount of memory in the page cache. It's too big of a hammer to really set to any other value besides 100 by default, because I wouldn't want to affect the average running system. But especially for databases and so forth that were swapping, even though there was plenty of memory in the page cache they feel they could reclaim, I introduced this Procsys VM page cache. It's no longer in rel 6 because of the split LRU and because of Cgroups and so forth. We have a different solution of preventing swapping and reclaiming page cache memory instead. And this is just a picture of how it works. Basically, if the page cache is over the limit, it would just, if the page cache is over its limit, when it deactivated the page, rather than just sticking it back here, it would stick it ahead of all the anonymous pages that were here. So it would force the system to reclaim page cache pages instead of anonymous memory pages. Zone reclaim mode. This is kind of a weird one, and you'll see this in the. Do you guys set this in any of the TuneD profiles? Back a while ago, I talked about when on a NUMA system, you've got kind of a choice. You've got, say, for instance, you've got 2 nodes, and you start a program. A program would comfortably fit in a node, but the memory in that node is allocated. So, say, for instance, it's an 8 gig node. Half the memory is allocated, so there's 4 gigs free, and you run a program that needs 6 gigs of memory. It would exhaust the node that it's running on, and then it's got a decision. It says, should I just start allocating from another node and force the program to run slower, or should I force the system to reclaim memory from the local node and cause the program to start up slower, but then be able to run faster when it's actually in memory and going. So we actually have, the system has a parameter called Proc.sys VM zone reclaim mode. And this is set to 0, which means that it will just simply go and fall over to the next node in line unless it thinks the internode memory reference times are too high. If it thinks the node reference times are too high, it looks in that table that we had. It's called the slit table. It looks in the table. I don't know if I have an example of that. Or no, I don't here. It looks in the table, and it says if the cost of doing cross-memory references exceeds the benefit of a quick allocation, then I'm going to force the system to reclaim. So you can actually have systems that are swapping and reclaiming memory, and you look at VMstat, and there's a ton of free memory. And the reason that we'd be doing this on the NUMA system is because zone reclaim mode was set to 1 by default, because at boot time it determined that it was better in the long run to do this, yet it's swapping. Right. So if you have an application...
So the trade-off is, indeed, do you continue to allocate memory and pay the NUMA cost? So our default will let you spill over. But in cases where you're controlling things, maybe with Cgroups or with
or if they're long-lived versus short-lived processes, right?
And or maybe a very fast paging, right? So traditionally, the NUMA cost is less than the page reclaim cost. But again, we've seen applications and people want to have this ability to turn this on and off, and so that's these are all in /proc/sys/VM. Zone reclaim mode.
And a lot of these ones that I sort of chose here are ones that you will see in the TuneD profile.
So these next two, so we do not mess with the zone reclaim mode in a TuneD yet. It's clearer if you have an app, you go home and say, hey, this really worked for our setup and for the way we've done our applications. You can either put it there or put it in the sysctl. Most of these parameters are all, okay, so this shows the path, Proc.sys VM, and you can set them in sysctl.
So the next two control how, so there are, like the page reclaim, the dirty write back from the page cache is controlled by 2 parameters, dirty background ratio and dirty ratio. And the way the system works is it allows you to dirty up the page cache. It's a write-back cache. It allows you to just write into the page cache until you hit dirty background ratio. Once you hit dirty background ratio, the system wakes up these background demons that start writing data back to the disks. By default, it's 10%, and you can control whether it starts earlier or later, depending on the performance that you're looking for. And this is a common thing to set in the TuneD profiles. And you can actually control it as a ratio, which is a % of memory. So you can say I want 10%. And then once systems became really large, terabytes, we support multiple terabyte systems now. Even 1% of a terabyte is a lot, especially if you have a system that is really unbalanced, that has a really crappy I/O system or whatever, or a very slow disk because you really don't want it to be doing a lot of I/O. It wants to do everything memory-based. You might actually want to set these background ratios lower than 1%. And you do that, you can't go any lower than 1 with the ratio, but you can go lower than 1% by setting something other than 0 in the dirty background bytes, and then that takes into effect.
What's the style
You can talk about the TuneD profiles and when these, can you?
Yeah, so in general, what we tend to do is the defaults are pretty high. They're going to try to start flushing data out, and it really depends on your storage. So it's a balance of storage, whether you want to dirty up or dirty down is kind of a way to do it. So most of the TuneD profiles have lowered the values so that you can essentially start the flushing a little earlier for like throughput loads and stuff.
But if you're going to like delete the files before it even gets a chance to write them back to disk, you'd probably want to do the opposite, right? You probably want to increase it so it just doesn't, if you know the program is going to create a bunch of temp files, kernel builds are a good example of that. It creates a bazillion temp files that compilers do. And if you increase this, it does almost no I.O. because the object files themselves are fairly small. It's the intermediate temp files. It's 20 minutes, by the way.
10 more minutes.
We got until 5:40, 4:40.
Oh, okay. So is there 10 minutes or 20?
20.
Okay, good.
Okay. So, and then so there's another threshold called, similar to the way the page reclaim works, there's another threshold called dirty ratio. We had a dirty background ratio and a dirty ratio. This is the absolute percentage of dirty page cache memory the system will allow before it stops the process and it says, you start writing dirty pages back. This is a throttling mechanism. So so it's a two-tiered approach. Once again, if you lower this, you will do a lot more I.O. If you increase it, if you lower it, you'll do a lot more I.O. but have cleaner page cache memory. If you anticipate running out of memory and need it reclaimed or something, then that would be the time that this would be low. Or that's when your TuneDs would set this too. And then once again, like the dirty ratio, you can only go down to 1%, and on massive memory systems, there are cases in which 1% is still too much, so you can control it in bytes. And then this is basically how it works. You start off low, you start writing file system writes, and you're sort of living down in this area of dirty memory. By the way, there are update daemons that run like every 30 seconds that keep stuff flushed out. So just the very nature of the system flushing its dirty memory back to disk on a lightly loaded file system, this may never kick in at all. But if you impose a heavy file system load, you'll exceed this threshold. At this point, doing a file system write wakes up these background daemons. And once again, there's one per LUN or file system. If you have several processes of threads all writing at the same time, it's possible to push this up even higher and exceed this level. Once this happens, the processes don't get to go up here. They actually do get to go up here. They do asynchronous I.O. So what happens, before it will let you exceed this limit, it says you have to stop what you're doing, collect up a bunch of dirty pages, and then throw them out to the disk I.O. system, and then I'll let you go. So it's possible to live up in this area, but the system, when this starts to happen, you get really heavily loaded devices, and it doesn't spend a lot of time up in this area.
Did one of your earlier slides say dirty ratio was 40%?
Yes, on RHEL 5, the numbers were 10 and 40, and on RHEL 6, they're 10 and 20. They were lowered because of the addition of the multiple flush daemons in RHEL 6. Yes, that's right. And then there's another mechanism of and this, generally speaking, isn't a good thing to do on a production system. But especially if you're doing benchmarking, rather than rebooting and putting the system in a known state between running benchmarks, you can manually flush the caches, either the page cache or the slab cache, by echoing a bit mask into this drop caches. 1 is drop the page cache, 2 is drop the slab cache, and 3 is obviously both. And basically you can see what happens if we drop the caches. You can see the page cache is big and fat here, and the buffer mem too. They're basically both the same, one and the same. But the system all of a sudden will just shove a bunch of, in this case right here, the memory wasn't dirty, so you didn't see a lot of I.O. taking place. It was just contained a bunch of old file system data that the files are closed, nobody's using. But if you wanted to get rid of it all real quick, it drops it, and you can see all the memory that dropped from here went right to the free list. Once again, you probably wouldn't want to do this on a production system because it's got to read all that data back in. You can do the same thing in the slab cache. The slab cache has what we call reclaimable and unreclaimable portions. Echoing a 2 into this parameter will drop the slab cache. I don't know if I put anything on here. Yeah. You can see when I did this, the slab cache just dropped by some amount. And the reason it could not drop it as dramatically as the page caches, there were a lot of kernel data structures you can't get rid of. They're the task and memory structures of running processes. The only thing it can get rid of are dynamically allocated data structures that are not in use anymore, and that's like the VFS caches and so forth, the file system caches. All right, so the next section here is maybe some performance tools, and I think you were going to start on that.
Yep. Right, and so again, these are probably common tools. Not going to spend a lot of time going through stuff. We'll try to highlight a few of the switches and knobs we use when we go through these. So, quite frankly, these are a lot of standard Unix tools. So there isn't too many. In fact, very very few Red Hat specific tools. Some KDE monitors down below and stuff. But really, it's top VMstat. I'll just say starstat because we've been adding lots of different stats. I just talked to you about NMstat and NUMA stat quite a bit. So again, I'm going to rock it through these VMstats. We kind of went through the example before of doing I/O. Make sure you look at the block in, block out. So there's per node values you can set with VMstats. So read the man page on that. In I/O stat, it's very useful to use the -X flag to start exposing the average request sizes being used. So most of your I/O gets better when you can get more aggregation, because then your physical disk and stuff have been usually well optimized for those cases. You can also look at the average queue sizes. So if you have an application, async I/O or something that can queue up the I/O, you can tell if you're doing synchronous I/O, you'll see an average request size of only like 1 and things like that. So in SAR, again, a whole litany of different switches and flags to set. Generally with SAR, we tend to collect a whole, use the -A option to do all the stats and write them to a file potentially, and then you can replay them. There's tools like KSAR that can show the graphical, or else you can write your own scripts to then later replay the SAR file. I like viewing on network stats with SAR because it's an easy way to see your send-receive packets and both packets and bytes, and so you can get to that information with net stats out there, but it still makes you do some calculations between intervals, so it's not as handy. And a whole litany of network tools. There are entire sessions on this. In fact, when we get into some of the other performance tools, I hope that if you were interested in a lot of the profiling and optimization, there's been a couple of excellent talks this week, but we will go through some examples. So one of the things in top today, you again, do a -H and you'll get like a whole list of options, but if you hit a -1, you get to see the threads. So if you're on a server with 160 cores, I find that you do a -1 and you can't see all the threads because there's 160 cores, and partly because I have glasses and need every year bigger glasses. So MP-stat can actually dump the per CPU cost out very easily. You also get to see things like interrupts and soft RQs and things like that, and so it's really useful to tune and optimize. And so a lot of people with big systems, make sure one process, one application isn't, if it's sitting there 100% pegged and it isn't multi-threaded and it's your log writer or you name what important process it is, no matter what other tuning you do, you may just not be able to go further until you figure out how to distribute that across or increase your threads or your tasks, etc. Again, we went through a lot of the free and the NUMA stat info. Again, look for NUMA stat to add a per process example and a little literally dump out per node and per process information now in a RHEL 6.3 errata or a RHEL 6.4 version. So NUMA stat, very powerful. Again, we're using this type of capability when NUMA D got built and invented, and interested to see whether you guys can gain control by essentially manipulating where your processes are running on these different NUMA nodes. I'm just going to finish up. So at the very end of this, so Larry's going to go through very specific tools that are in the how to read the Proc file system. And this is where your eyes might get, you might have to squint a little to come up, but essentially we do have the slides available. And if time permits, we'll go through some O-profile, system tap, and perf examples. But again, that's something that was covered in Will Cohen's talk, or see us afterwards. It's perf, if you haven't used it, is a very powerful tool that can give you lots of on-the-fly profiles, deep profiles, and system stats.
Okay, so I just wanted to talk the Proc file system. Proc file system is a portal into all the kernel's internal data structures. You can see a lot of detail about what's going on in the kernel, actually too much, and you just kind of have to know sort of what to look for here. So the first thing, proc meminfo, I just sort of showed how it was increasing between RHEL 4, 5, and 6. And in the case of meminfo, I think I said this before, you can see where we talked about all the split LRU, active, inactive, and all this stuff. You can see the summation of all the different number of pages on the LRU lists and all these states. In addition to that, for a NUMA system, you can go into the sys file system and see where they are on each node. Most times, most people wouldn't really need to do that. When you'd need to do that is if you're trying to literally bind memory to certain nodes in order to really optimize some performance. The slab cache, I think I said this before, it's a cache of kernel data structures. There's not a lot you can do with it, although there is, I didn't want to say too much about this, but there is some tunables. You can control how aggressively the system, when it needs to replenish one of these caches, how aggressively it goes out and grabs big chunks of memory and divvies it up and so forth. CPU info just tells you all the CPUs. There's really not much to say about that. In the Proc file system, each process ID has an area Proc PID number, and in there you can see anything that's mapped in the address space. Something that's really valuable now, especially tuning a NUMA system, is what they call the NUMA maps. You can go in and see different regions of virtual memory, how many pages are mapped in there, and which nodes they're coming from. This really makes a huge difference when it comes to trying to optimize, or do benchmarking and really get the optimal performance, and to verify that your bindings, that NUMA CTL or Cgroups, however you're doing this, is working, and to verify that tools or daemons like NUMA D are actually doing what they're supposed to be doing. There's a whole subsystem, so to speak, that you can, when a system gets really busy and really hard to figure out what's going on, you can actually get in underneath the operating system, so to speak, and then say, I want to know what the hell this thing is really doing. And it's called AltSSIS Wreck. You can either run it out of the command line, or you can do it from the keyboard, and it will allow you to look at, back traces of processes and memory specifics and so forth. An AltSSIS Wreck, and this is obviously really small, but it actually will show you on each node exactly where every page of memory is. I chopped off a bunch of stuff up higher, but it'll show you what CPUs are doing and what all kinds of other stuff. This is how you really get down and dig deep and figure out what's happening. It'll give you how well the coalescing of pages is taking place. So somebody had asked me before about making sure the system is coalescing enough memory to allocate huge pages. There's other ways of doing it, but this is how a kernel nerd would do it, is to get in here and look and really see how many pages have migrated over and so forth. This, once again, the sys file system, you can look at this, you can see the LRU queues on a per node basis and see, and the reason you'd want to do this is only if you were benchmarking, you really wanted to get down into deep and dirty and see what was going on. AltSys, you can get trace backs of processes if you get a process that's stuck, you don't know what that thing is doing, you can get in there and figure out what it's stuck on and so forth. Obviously, this requires quite a bit of intimate knowledge with the kernel or the libraries or whatever that it's stuck in. You can say, I want to see what every running CPU is doing, and so send messages to all the running CPUs to tell them to dump out their stacks and so forth. Once again, this is how you debug serious problems, kernel problems. Next thing I want to talk about is OMKills. Have people run into OMKills much in the past? Basically, OMKill, the system is out of memory, it's backed into a corner. In this case right here, let's see, this was somebody, before we a little bit, 32-bit systems had a serious problem that was hard to work around called low mem consumption or low mem exhaustion. Low mem on a 32-bit system is where all the kernel data structures come out of and all the kernel memory is. You could easily allocate all of the low memory on the system and not be able to free it up, and then the system has to OOM kill or try to kill a process so that the process's kernel data structures would be freed in order to keep it from going on. Once it gets to this point, it has three choices. It can either kill a process, or one or more processes, it can hang and do nothing else, or it can panic. And what it does by default is to kill a process and to print a message out to the screen. And these are just a couple examples of if you had an I/O system that just wasn't working. In this particular case, I think I had a NFS system, and I literally pulled the link out of the box. So the server couldn't reclaim anything, and I just kept the memory load going and going and going. And it just, and what happens is it OOM killed because it couldn't reclaim any of the NFS pages. How you eliminate OOM kills on RHEL 4 and RHEL 5, I put a tunable in called I think it's OOM kill, or OOM in Proc/sys VM. And if you shut that off, the system wouldn't OOM kill. It would hang, or if you could set another parameter to say, I want it to panic if this happens. There are times in which this would be useful because you could imagine transient conditions in which the system was under a massive load for a couple seconds or whatever, and this condition hit and an OOM killed. But if you just sort of got through the bad time, so to speak, and got to the other side of it, then it would recover and sort of just do its own thing. Well, in RHEL 6, so much has changed, that really wasn't a feasible option. So basically, there is, in the Proc file system in PID, there's something called UMAdjust, which is kind of weird, but it's kind of like nice, is you can set a process up to, in sort of predetermine who's going to die if they need to die. You can basically commit suicide and say, and this works just like nice. If you set this thing to a high value, the system OOM kills, it's going to pick the ones with the highest ones. If you set it to a negative value, it isn't going anywhere. Yeah.
Is it only available for RHEL 6?
Yeah. Yeah.
This feature RHEL 6 and up?
Yeah. Yeah.
I'm pretty sure you can set OOM niceness in RHEL 5, right? I played around with it in RHEL 5, that's what I'm saying. The problem is...
Yeah, I'll have to look. It's been a while.
The problem is you can't do it dynamically, right? So unless you know ahead of time
right.
where your process IDs are going to be, or you have a way to scan for the process table and
Yeah, it's really meant, a lot of these Proc file systems are meant for tools that are layered on top of them. And I'm not sure exactly. I'm very comfortable echoing stuff in the Proc file system, but a lot of, it's probably not a desirable thing to do, but You sort of become used to it, especially when I added some of these things. So I feel more comfortable than other people doing them. So, but this, it's sort of like nice in that you can sort of give yourself up, so to speak. And then,
So in fact, I think perfect timing. The number for this game, which is
for this session,
is 1351. We'll stick around if there's any other questions. And again, here are your last set of slides.